Hello everyone. So change of topic from simulation now to multi-messenger cosmology. I'm Suvodip, a postdoc currently at IAP, Paris. So I'm going to talk about a new method, a new probe to explore cosmology using several multi-messenger probes which are coming in the upcoming decades. So when we say about multi-messenger paradigm, the structure is now getting more and more transparent to us by multiple probes. Of course, one of them we always using for the classical ways, like using photons, the electromagnetic waves. 2 years back, we have discovered gravitational waves, and we have also simultaneous measurements of neutrino events. So we have seen photons and gravitational waves together, and from the neutron star event, there is similarly a blazar event which has seen gamma rays and neutrinos. So we're now entering into a phase of doing multi-messenger astrophysics or cosmology. So when you say about cosmology with gravitational waves, the standard picture comes to mind is this. We have a standard sirens. Compact objects are excellent tracers of distance. If we can know its redshift independently, we can fit the luminosity distance redshift relationship, and we get the cosmological parameters. So to get the redshift, if it is a binary neutron star or binary black hole neutron star, we have an electromagnetic counterpart. And indeed, 2 years back, LIGO has measured this signal, the neutron star event, and from that, they've obtained the first constraint on H0, which is shown over here. For black hole binaries, we do not expect to see electromagnetic counterpart for LIGO frequency band. So we expect to do cross-correlation studies between binary black holes and galaxies to do the redshift luminosity distance and test, as mentioned by Ben Wandelt on the first day. So I'm not going to talk more on this topic, but this is basically a cross-correlation of the overlapping galaxy survey with the black holes you see. But if you now think about another way of doing cosmology with gravitational waves or multi-messenger cosmology, along with the standard sirens, we have when any compact object event goes off, the gravitational wave phenomenon happens, we have all the density fields which similarly affects your signal. It affects the gravitational wave strain, or it also affects the gravitational wave frequency. So what can we learn from that? So this can be another approach to learn about cosmology. And my talk is going to be about that. So talk is about how can we infer the imprints of cosmological signal from individual gravitational wave sources. So I will talk about how we can do it, one of the ways, there may be many other ways we can do it. Then we'll talk about when we can do it, and then I'll talk about why we should do it. So this work has been done with Ben and Joe, and it's under review currently. So let's talk about how at first. So if you calculate the effect of cosmological perturbations on gravitational wave frequency and strain, the effect can be explained in terms of the observed frequency will be dependent on the perturbations along the line of sight, which will depend upon the Sachs-Wolf term, the Doppler velocity between the emitter and the receiver. So the R is at the receiver ends and the E is at the emitter frame. And this is the integrated Sachs-Wolf term. So you will see some distortion in the frequency. You will also see a distortion in the amplitude, which is primarily because of the lensing signal, which one can write in terms of the density field for a given line of sight. So you are observing a black hole binary, you are asking along that line of sight how much perturbations are there, and the integrated effect of that affects your total amplitude or the gravitational strain. And we are after this signal now. This signal is weak, of the order of 10⁻⁵, the fluctuation. We are talking about this signal in the rest of the talk. So how we do it? The idea is we have to see another probe which is seeing the same lensing structure. So let's take a binary black hole merger, which is emitting gravitational wave, which gets bent because of the structures, and it gets lensed, so it gets bigger, the strain gets bigger. In the same geodesic, you have photons which will cover, which will propagate, like CMB photons. CMB photons gets lensed, there's a weak lensing effect on CMB photons, and they traces the same density field, the same trajectory. So the question now we're asking, can we use this method to explore the lensing signal from gravitational wave? The method is CMB-GW correlation. So how it goes? So CMB, so this was mentioned by Shurhut in the first day. I will just briefly mention it over here again. So when the CMB photons from the surface of large scattering ring propagates to us, it interfaces through a lot of structures and it gets lensed. And the imprint of this you can see in the temperature field. So you get, so if this is the lensing potential, you see a distortion in the temperature field. You also see a distortion in the polarization field, which we write in terms of E mode and B mode polarization. So you generate lensing signal in E mode, and at large L or at small angular scales, you generate B mode polarization. The gravitational strain from individual objects have a slightly higher strain when it is lensed, or not, or it is a reduction if it is coming through lack of objects along the line of sight. So the idea is we correlate the waveform, observed waveform, with the CMB signal or the CMB polarization and the temperature signal along from one point to all other points as a cross correlation study. So we have individual objects. Let's take a simple example. This is the Planck lensing map 2018. The blue one are the high density regions, the yellow, whitish one are the less density regions along the line of sight integrated mass. And let's say these green balls, so we have multiple GW observations, primarily from binary black holes also. Yes. Okay. So the idea is how can we measure the correlation between them? So the idea is the correlation between the gravitational wave signal and the CMB signal between all possible angular scales, we are going to measure, and the signal and the within this blob are going to be smeared because of the localization area. So within a small area, if I have any cosmological signal, that will not be able to measure because it is smeared by this by the sky localization area. It's like a beaming effect. So if we do that, you can think about an estimator. That's what I do. That any gravitational wave sources have a DL, luminosity distance map. You can make out of it of all the samples of gravitational wave sources, and you correlate that with the CMB kappa map. So any overall error you make because of unknown in the parameters on the redshift dies down because CMB kappa field do not correlate with any additional noise term. So only the cosmological signal of gravitational wave correlates with CMB. And this is the signal we are after. So how the signal looks? So if you take gravitational wave sources in individual redshift bins, like say redshift 1, redshift 2, redshift 3, and so on, and ask within the standard model of cosmology, and assuming GR is correct, how the signal, the RMS fluctuation of this signal looks. This is the signal predicted. We can calculate for as a function of redshift for gravitational wave correlation. That's the red line over here, and this is the correlation between CMB and gravitational wave. This is the blue line over here. So the idea will be we want to measure this cosmological signal from the gravitational wave sources, individual gravitational wave sources. So the thing I talked about here is basically this correlation, which is given by the matter density field, and the transfer kernel of gravitational wave sources and the CMB weak lensing. So the measurement is possible from a wide band of gravitational wave, multi-frequency gravitational wave measurements, from terrestrial like LIGO India, Virgo, LISA, Cosmic Explorer, which is a future experiment. Also like LISA, which is a space mission observing low frequency gravitational wave. So we can use both these sectors now to estimate this cosmological signal, use this lensing cosmological signal from the individual gravitational wave strains. So how will they go in redshift? Why are we choosing them specifically? So if you see the paper from LIGO, with the advanced LIGO measurements, they're typically going to hit around redshift 1, the measurements. With future upgrades, they are possible to go maybe up to redshift 2 to redshift 3. So we are going to get a lot of overlap with the cosmological signal. And also, after LIGO India, Kagra starts, the sky localization area is going to reduce to about 10 degrees. So the correlations, as I already mentioned, a better sky localization area is good for the signal to measure. So we'll improve the signal to noise ratio of this measurement. So the way to do it is we have a lot of cycles of the gravitational wave signal. The SNR for the signal can be written as in a simple form as this, where this is the noise power spectrum, this is the signal power spectrum, this is the corresponding frequency. You correlate this to signal. And we ask how much we can get it. So how much we can get it will depend upon how much noise of the future experiments are. So here comes the question of when we will be able to do it. So with the advanced LIGO noise showed by this dash line here, or the Cosmic Explorer, which is a 40-kilometer baseline LIGO detector being proposed now, which is called Cosmic Explorer, we are going to see about tens of hertz to 100 hertz gravitational wave sources from ground-based experiments. For LISA, this is going to be about, with the mean frequency around 10 raised to minus 2 hertz, we're going to explore about like 10 raised to minus 1 to 10 raised to minus 4. So mass range now we are talking about for the black holes are like tens of solar mass, hundreds of solar mass to 10 raised to 4 to 10 raised to 7 solar mass objects. All these gravitational wave sources are seeing the lensing and seeing the same lensing field. So we want to measure them by combining the mass, all the masses coming from either LISA or from the ground-based experiments. So how the discovery space looks with LISA? So I'm talking first about LISA because it has maximum overlap with the kernel because LISA goes very deep in redshift. So if you plot the cumulative signal to noise ratio of the measurement of the CMB and GW cross correlation as a function of redshift, this is how the plot looks. So these are obtained for different numbers of gravitational wave sources. So the dot line are for 300 gravitational wave sources per unit redshift bin, and the dash line is for about 50 per unit redshift bin. So this plot is obtained for 10 raised to 4 solar mass objects. So we take the waveform, which is up to not the only the inspiral phase, not the merger phase, and we estimate the signal to noise ratio from the inspiral phase and the correlation of the lensing. For the terrestrial detectors such as Cosmic Explorer, the measurement for typical mass value of like a few tens of solar mass, we are going to hit above 10 sigma measurement. And so the point now comes is if advanced LIGO gets in with LIGO India and Kagra, then this measurement even at redshift 1 or 1.5 is getting possible with typical numbers within 5 years of time scale from the measurements. So we are going to have a lot of binary black holes, and we are going to cross-correlate this with the CMB signal. So I basically talked about this part where we have individual gravitational wave sources and GW lens, CMB lensing and galaxy lensing. The other part one can always explore about the stochastic gravitational wave background, but that I'm not going to cover here. So now the point is, why are we going to do this? So this covers a lot of interesting science goals. I'm going to list a few of them here. One of the important part is that the photons and the gravitational wave follows the same geodesic. This we can also explore by this method at the perturbative level. So one can think that as the perturbed geodesic of the CMB photons are same as the gravitational waves for a particular line of sight. And we're going to cross-correlate that. The other information you're going to get is the lensing signal itself of the gravitational wave. So this one can think about as like a graviton scattering kind of concept. Now if we have a measurement of this thing for a large number of objects, the primary idea will be to delens the signal. Because the measurement of the source parameters of gravitational wave sources, if you do not have independent redshifts of them, the mass gets biased because of lensing. If we can correct for that by using this method, that will be extremely cool. On top of that, when you talk about fundamental physics measurements, such as any alternative theories of gravity, they affect the propagation of gravitational wave by this equation, where when nu equal to 0, c t equal to photon speed, and this is equal to 0, this is equal to 0, we get GR. And the recent binary neutron star event basically constrained this value. The speed of photon and speed of gravitational waves are same. The other thing we are going to explore now by this method is about the damping of the signal along as it propagates and the anisotropic stress part. Because lensing is highly degenerate with this kind of quantities, we need to remove the lensing signal accurately to actually get into estimation of alternative theories of gravity. So I don't have any time, so I will stop here. So I told about a new signal which we can measure using cross correlations between CMB or gravitational or galaxy distributions with the strain of the gravitational sources. With the typical sky localization area we expect after LIGO India starts, we are going to make a measurement of about, depends upon the number of objects, going to make at least after LIGO India about 2 to 3 sigma measurement is possible. But once it is like 8 to 10 years cumulative, we are going to make this measurement more than 3 sigma with advanced LIGO sensitivity. So I'll stop here. Thank you.
While we set up the next talk, we can have one question. Yeah, one or two. Yeah. Yeah.
You concentrated mostly on CMB lensing, but as you mentioned, the CMB lensing kernel peaks at redshift 2.
That's right.
Whereas the advanced LIGO curves that you showed, the SNR seems to increase with lower redshifts.
Yes, so
why not use
between only redshift 1 and 1.5?
Yeah, why not use galaxy lensing, cosmic shear?
Same thing. So I talked over here on CMB, but we can also use LSST or Euclid distribution,
right.
distribution.
Yeah.
Do the same concept. So I just talked here about the CMB part, but the method is exactly same for galaxy lensing.
Right, and why stop at lensing? Cross-correlate with galaxy.
No,
right?
so that part we have done. So that's the part where you can correlate galaxy distribution itself
right.
with the binary neutron star or binary black hole events to get the redshifts. That's the clustering part. That we have, so I briefly mentioned about it.
Okay, so let's thank Suvodip. We can ask questions during the talk.